welcome to the 11th lecture. So today, as promised, we are starting a new topic called the Lovasz local lemma. Some people just call it the local lemma, but this is, in fact, Allen and Spencer just calls it the local lemma. We'll use the Lovasz local lemma because it also has this nice abbreviation as a triple M. Okay. Now, this before telling you what is the lemma, let me tell you where, what is the context, where does it stand. Okay. So, in one line, I can say that this turns out to be a better choice than the union bound. In some cases, it turns out to be a better choice than the union bound, and we will see where. Okay. So, consider a scenario. We have seen this scenario many times in this course. It's a very common scenario where we have m events, A1, A2, etc. And due using some calculation, we established that each of this event has a probability at most p. Okay, for each I we bound the probability of the event ai from above by some very small number p. Generally, this p is going to be a number very much less than 1. And what is our aim? Our aim is to show that the union of these events also has a probability small. But there, generally, we do not really care about how small, and that quantitative bound on the union. The probability of the union is not very useful for us. We only want to show that this is strictly less than 1. Because after this point, we are going to make our philosophical argument that if the probability of this event is strictly less than 1, that means there exists somebody in your sample space which does not, which is outside all of these events. So if all of these events are, each event generally is one way for a thing to go wrong, and the union of all of them is all possible ways of them going wrong. If that event has probability less than 1, there is still one way at least to get it right. So here, this you already know. I only want to emphasize that here this less than 1 is all that we require. Okay, we do not really care about how much it is needed. And then what do we use? If this p is sufficiently small, in the sense that if p is smaller than 1 by m, we can get this kind of a bound by applying the union bound. What do we use? We use the fact that the probability of a union of some events is upper bounded by sum of their probabilities. And now, since each probability is upper bounded by p, I can substitute a less than or equal to mp here. Okay, and this inequality here is known as the union bound. So what's a good thing and bad thing about this union bound? The good thing is that you don't need any assumption of independence between the events a1 to am. Okay, this union bound works unconditionally. You don't need any further assumptions. The disadvantage is that when the collection is very large, when the number of events m is very large, you need a very small probability p. Your p has to be less than 1 by m for this to work. Okay, so this is the scenario 1. Now let us contrast it with another scenario which is kind of an extreme opposite. But this scenario is not that common. That's why I have kind of hinted in brackets that this is a rare scenario. But here again you have m events a1 to am, but you have this additional assumption that they are all mutually independent. Okay, in fact that's the only difference between scenario 1 and scenario 2. Okay, yeah, in fact I just copy pasted it and wrote this mutually independent case. Okay, and here in fact you won't even need this. I'll strike out this much less than 1 after you see why. Okay, and again, so the scenario 2 is where the collection of m events is mutually independent. So here I am assuming you are conscious about the difference between pairwise independence and mutually independent. Even among 3 events, it is possible that any 2 of them are pairwise independent, but when you take all 3 of them, there is a dependency. Okay, you can easily set it up by taking 3 events where you toss only 2 coins and then say that event 1 corresponds to the first toss being head, event 2 corresponds to the second toss being head, and the event 3 corresponds to something which says that number of heads you obtained was an odd number in the previous 2 tosses. Okay, so if you you have to, if you already do not know this example, please pause and think about this example. Here any pair, not just the first two, not just let's say A1 and A2, even A1 and A3 as well as A2 and A3 are independent. But if you take all the three, they are dependent, because once you know the first two, you automatically determine the third. Okay, so this mutual independence is a very strong collection, which in some sense means any subset of these events are independent. Okay, but this is, in practice, this is most of the time this is obtained. Okay, it turns out that these examples where you have pairwise independence but not mutual independence is a bit rare. So that is why for an applied probability theorist, you kind of fail to distinguish this difference between pairwise and mutual. Okay, but for this scenario and this analysis to work, we need this stronger notion of mutual independence. Okay, and second stage is the same. We have already bounded the probability of each event by some p. Here in fact you don't need this p much less than 1, we will see why. And we want to show that the union of these events has a probability less than 1. Okay, let us, instead of using the union bound, let us use the De Morgan's law. So we are interested in the probability of the union of these events, which means it's equal to 1 minus probability of the complement event. But now the complement of a union by De Morgan's law is the intersection of the complements. These are not inequalities. These are in fact set theoretic equalities. And now we are going to apply independence here. Since AIs are mutually independent, you can verify that even the complements of AIs are mutually independent, and hence you can exactly calculate the probability of this intersection as the product of the probabilities. Okay. Now here I should actually be careful. I should not. So this much is here we have. This is where you have used independence. In fact, the independence tells you that this term here is equal to this term here. Okay, that's where we have used the independence. In the next step, we have to be a bit careful about the inequality here, because p is an upper bound for each of the probability. So 1 minus p is a lower bound for each of these quantity. But again, because of the minus sign here, this minus 1 minus, this all works in the correct direction. What I want, since I want to put an upper bound here, I have to put an upper bound for the negative this quantity, which means I have to put a lower bound for the product term, but I have a individual lower bound for each term in the product, which is 1 minus p. Okay, again nothing sacred here. If you are confused, pause and verify. Otherwise, just believe me that this inequality is in the correct direction. Okay, and this quantity here, what do we want? We want this to be less than 1. That's all that we care. Okay, remember, all that we care is that this guy here is less than 1, and in order for that to be less than 1, you just have to subtract out some non-zero quantity. Okay, and this p, as long as it is less than 1, this quantity that you subtract out is non-zero, and hence you get strictly less than 1. Okay, that's why in fact I striked out the much less than 1 here. Now you only need a p less than 1. Okay, but now remember, your p didn't even have to depend on m. For the union bound, your p1, it would have worked only if p was less than 1 by m. Here you really only need p to be less than 1. Okay, you only wanted that none of these bad events will surely happen. Okay, so you should probably read this qualitatively also. If you have m mutually independent events, and let's say call them bad events for the sake of analogy, and you know that none of these bad events are sure events, okay, which means all of them has a probability which is upper bounded by some quantity less than 1, strictly less than 1. If none of them are sure to happen, then we can conclude that even the probability that all of them happen is less than 1, okay, which means there is a non-zero probability that none of these events will happen. Okay, you did not need the m anywhere. You only kind of use the fact that m is finite in some sense here. Otherwise, this m we did not use. So what is the advantage? As we mentioned, we only need to bound P to be less than 1 as opposed to 1 by m in the union bound. But the con is that we need this heavy independence. Okay, we need independence, and that to the strict version we need a mutual independence for this to work. And now this sets the stage for bringing in Lovasz local lemma, which kind of sits in between. Okay, what do I mean when I say that it sits in between? This is, consider this third scenario. In fact, it's a very common scenario. So this Lovasz local lemma gets applied quite often. Okay, so here your collection of events A1 to AM is partially independent. Okay, I'll define what this partial independence is in a moment, but notice that rest of the scenario is the same. All that I changed is the mutual independence. I kind of replaced with some undefined term, partial independence, which I'll define now. Rest of the story is the same. We have an individual upper bound we have individually upper bounded all the quantities, and we are aiming for an upper bound on the union bound. Again, we only need it to be less than 1. That value of this is not significant, apart from the fact that we need it to be less than 1. Okay, so now let us come to the crux of the matter, which is like, what is this partial independence that we are talking about? So this partial independence that we are talking about, okay, is that for each event AI is mutually independent of. Okay, so the word mutual says, but what is the extra relaxation that we are giving? We don't want it to be mutually independent from everybody, but we want it to be mutually independent from everybody except at most D. Okay. Now, intuitively, there is some there is some issue of rigor in this kind of a model, which we will talk about later. But intuitively, or in a very approximate sense, what we are saying is that each event AI or the event AI depends on at most D other events in the collection. Okay, each event AI depends on D at most other events in the collection. Now, what is the problem with the rigor of this intuitive understanding? That you may misinterpret this to say that now, okay, you allow these D events which on which AI depends. That's fine. Now you start checking for every remaining event. You start checking pairwise. Okay, so now you take the first event outside of this collection. Okay, AI is independent of that. Fine, you check mark, right? And if you finish this off, that won't be correct. Okay, because outside of these D events, you again need this mutual independence, which means this event together with any subset should be independent of any subset of the remaining events. Okay, so how does one say this formally? It is like for each AI or each I element of M, we should be able to find a subset of indices. Okay, in fact, we are going to just find a subcollection of events, but in order to for the notational convenience, it is easy for me to talk about a subset of indices, and then you talk about the collection based on that subset. Okay, so yeah, there exists a subset. This subset contains, yes, this is going to be the subset of events on which can have a dependency with AI. So that means you have to include I to S, and it contains at most D other events. Okay, that is why you have this D cardinality of S at most D plus 1, and this is a mistake. It's not for every T subset of S, but it is for every T. In fact, that's a serious mistake. It goes exactly for all T subset of M minus S. Okay, for any subset of the remaining events, the conditional probability of AI given those remaining events has to be just P of AI. Okay, so if you remember, this is one way of there are two classical ways to even denote pairwise independence. You say that this is equal to P of PB. Okay, this is one definition of pairwise independence. Similarly, you can also define it this way: P of A given B is this, right? Now when you are here in the, what is B here? B is the intersection of any subset of the remaining events, okay? So even if any you can, yeah, this is like what would have been a mutual independence when you had 3 events. If you had 3 events, for mutual independence you actually need 4 relations, right? This has to be PA, PB, PC, and then PA intersection B has to be PA, PB, PB intersection C has to be PB, PC, A intersection C has to be P, A, PC. Okay. Here there is a slight difference here. If you think about your A as your A1 and B and C as events which are in the set T or in the set M minus S, right? So here between them, between B and C, you are allowing some dependence. Okay, so this, for example, we do not care about. This guy we do not care about. We are not talking about that, but we are rather only talking about conditions where A is involved. Okay, that's why you have AI always, and for any other subset from this excluded collection, you can put it in the conditioning event, and this conditioning should be immaterial. Your probability of AI conditioned on this should be just the probability of AI. Okay. Now, yeah, this is a definition which takes some time to understand clearly, but in many examples, this independence is going to be very clear, because the mutual independence is going to be very clear, because you can see that even the random experiment which determines AI is completely disjoint from the random experiment which determines AJ for any J in this T. Okay, so even though at this stage it looks a bit confusing, don't worry. When you are trying to apply this Lovasz local lemma, the context is going to be much simpler. Okay, so let's get back to the scenario with this understanding of partial independence, right, or maximum D range of dependence. What is the conclusion? This is the scenario. You have A1 to AM with this partial independence. We have this bound for each event, and when can we show that the union has the probability at most 1? What Lovasz local lemma tells is that if this inequality is satisfied, so remember you should, E is 2.718, the base of the natural logarithm. This is the condition we are thinking about. Okay, ignore this +1 for a moment. What we are saying is that EPD is less than 1, or something like P is less than or equal to something like 1 by ED. Compare this with 1 by M. Right? M is the total number of events in the collection, whereas this is more like 1 by D with an extra constant of 2.7, which is okay. I mean, it's more like 1 by 3D, let's say. Okay, but this D is only the range of dependency. It's a number of events on which each event will at max depend. So this whole M now you could replace with this 1 by D almost, with this correction factor of 1 by E. That is what Lovasz local lemma says. Okay, so now let's state the lemma precisely. This is actually originally this is due to Erdős and Lovasz from 1973-75, but but it's mostly called as just Lovasz local lemma, because the proof of the more general version, which we will see in the next class, is due to Lovasz. Okay, so what is the lemma formally? Let A1 to AM be events such that these 3 conditions are satisfied. What are the 3 conditions? Each event intuitively depends on at most D other events, or more rigorously, because there is nothing like, why do I have to go to a different language when I want to make it rigorous? Because you have this very clear definition of pairwise independence and pairwise and mutual independence, but I do not have this notion of that distinction when I am talking about just dependence, okay, instead of independence. That's why when I want to speak in rigorously and use the word mutually, I have to talk about independence rather than dependence. Okay, so each AI is mutually independent to a subset of at least m minus d other events. Okay. Intuitively, it says it is dependent on at most d other events. I think it would be m minus 1 minus d, right? Because the number of other events is m minus 1 and it can depend on d of them, right? So this is m minus 1 minus d other events, and for each event the probability of its occurrence is at most p, and we have this analytic bound, your p is less than 1 over e times d, or 1 over e times d plus 1 to be precise. If all these conditions are satisfied, then the probability of the union is at most 1. Okay, so this is what is the formal statement of the Lovasz local lemma. So compare it with the union bound to see how stronger this is. The proof we will postpone for one class. We will see 2 applications of it, and then maybe we'll even see the asymmetric version of the lemma, where each event ai, the probability is upper bounded not by the same p, but by some p1, p2, etc. And then in this case you see that even if all those pi's are upper bounded universally with some p which is less than 1, we are done. But we will get a different expression for condition 3 in the asymmetric version, where each probability is upper bounded by some pi. And from that asymmetric version, this will follow as a corollary. So we will prove only the asymmetric version. Okay. So this last 30 seconds of blabbering is just to convince myself that I'm justified in postponing the proof for later. Okay. Usually it's something which I really hates to postpone a proof, but in this case it is for a reason. Okay. So in the rest of this lecture we will see 2 examples. First example is examples of applying the Lovasz local lemma. First example is about hypergraph coloring. Okay. So recall that we had seen this problem already when we were studying the first method, the basic method or the union bound method. What was the context? We remember what was a k uniform hypergraph? A hypergraph in which each edge contains exactly k vertices. Graphs are 2 uniform hypergraphs. And suppose the total number of edges was m, and this m happened to be less than 2 to the power k minus 1. Then using the union bound, the basic probabilistic argument, we had concluded that H is 2 colorable. Let me also remind what was 2 colorability. We are coloring vertices. Okay, not hyper edges. We are coloring vertices using 2 colors such that each edge sees both the colors. Okay, no edge is monochromatic. That's the idea. This is also known as property B. If a hypergraph can be 2 colored, it's also said, we also say that this hypergraph has property B. What was the proof? A quick recall. You were coloring each vertex independently and uniformly at random, tossing a fair coin at each vertex independently of the previous tosses. And what was the event ai? The ith edge was monochromatic. What was the bound we could give for probability of ai? In fact, we could give an exact value of PR of ai, which is half to the power k minus 1. Okay. Why? Because for all the vertices to be of color 1, the probability was half to the power k, but then you could also be all the vertices were of the other color. That's why the k minus 1 came in. Okay. Yeah. And now, what was the union bound? The union bound, this probability of union ai, which says there is at least one monochromatic edge, which we wanted to be less than 1. Why? Because we are looking for the opposite event, right? We are looking for a coloring in which there is no monochromatic edge. Complement event is there is at least a monochromatic edge, which is the union of these events. And since our m was cheatingly chosen to be less than 2 to the power k minus 1, these 2 guys multiply out and give something less than 1. So that was the proof, right? But now this would only work for m less than 2 to the power k minus 1. So for example, for graphs when k equal to 2, this is silly. This will only work when m is less than 2. For 10 uniform hypergraphs, looks okay. It will work for m less than 2 to the power 9, 512. Okay, but 512 is still a small number, right? So it's kind of a silly bound. But now, suppose m is very, very large, okay? But there is some bound on the edges, intersection pattern. What do I mean by that? I'm saying that each edge intersects with at most d other edges. Okay, so if you take any edge, each edge is a k set. Okay, so it may be, let's say k is 5, so it may have 5 other elements. Now what we are saying is that this intersects with at most d other sets like this. Okay, this intersection is at most d. These are also, remember, 5 sets. Okay, I hope I draw. Okay, anyway, the picture is not important. Yeah, these are the what I'm saying. Okay. This is different from the saying that the degree of the hypergraph is k. In fact, the degree of the hypergraph is d. In fact, if the degree of h was at most, the maximum degree was some L, then what is the bound that you will get on d? You can actually show that d is at most some L times L minus 1 times k, right? Why? Because you now focus on each vertex in a particular edge, the ith edge, right? So there are how many vertices there? There are k vertices there because it's a k uniform hypergraph. Each k of them, if you had a bound on degree by L, will participate in at most L edges, which means at most L minus 1 other edges. This edge it's already there, it can now participate in L minus 1 more edges, and each k of them will participate this. Okay, in this case the picture would be you won't have these common intersections or anything, but yeah, that's fine. But yeah, this is also good to know. I do not know why I was kind of glossing over this that much, but here the d that we are speaking about is not the degree of the graph, but it is in some sense the extent of dependency in the graph. Each edge intersects with at most d other edges. Okay, so here I want you to convince yourself, again want you to pause and think that the event ai, okay, what is the event ai? Ai is the event that the ith edge is monochromatic. Okay, I want to convince yourself that the ai depends on at most d other events. Okay, so why are we saying this? So here maybe it's a good place to see. Okay, let me draw this. Okay, I created some space to draw a picture. Okay, so here this is your ith edge. Okay, so the edge ei. Okay, this has k vertices, right? Now we see that it depends on at most d other events. These d other events correspond to those edges which have a non-empty intersection with ei. Okay, the d that we are talking about are those edges which have an intersection with ei. So what are the other guys? Depends on at most d other events. The other guys are edges like this, which in themselves may or may not intersect. These are the other edges. But what is the property? If you take any edge here, none of the vertices in that edge are shared by this. Okay, so this is almost on a different planet. Okay, the vertices that fall into these edges are different from the vertices that fall from here. So even the strong notion of mutual independence, whether this ei is monochromatic or not, you see that it is independent of any function of any collection of these edges, right? Because the coin tosses on each of these vertices are independent. So these k coin tosses have nothing to do with as many coin tosses that you have to do for these edges. Okay, so this is why I am saying this mutual independence, it's a strict requirement, but in many applications this is kind of clear. You take any subcollection of these edges, they have nothing to do with this. Between them they may have something to do, but they are independent of E. Okay, so this is this is one good illustration of the mutual independence. Okay, now rest of the proof is simple. Okay, it's a direct applications. We only need this Lovasz local lemma to be applied. We need this EP of d plus 1. Many of the people will just remember it as EPD less than 1, or even 4PD less than 1 is a more common way that people remember. The upper bound E with 4 and then this plus 1 also will not matter and all. But yeah. So EPD less than or equal to 1. Now you solve for what D will give you this, right? You want your D to be something like 1 by E 2 to the power k minus 1. So remember, the union bound proof also had a similar bound. The bound there was strictly less than 2 to the power k minus 1. There also in the union bound also, this we got 2 to the power k minus 1. But the difference is that the left hand side was m. Okay, it was on the total number of edges. But here the key thing to observe is that the left hand side is just d. That's the amount of dependency. Okay, so the dependency has to be less than this. Okay, then we are done. Okay, so for example, you can now to summarize, the result says that a k uniform hypergraph in which every edge intersects with fewer than this number 2 power k minus 1 by E other edges is 2 colorable. Okay, now yeah, this remark I wanted to discuss. That's why I noted, is a single vertex overlap okay? So let's go back to this picture. Okay, and consider this EI once more. Okay, now suppose there is another edge EJ which overlaps with one vertex of EI. Okay, so again the event that this is monochromatic and the event that this is monochromatic, that is AI and AJ, if you actually consider what is P of AI intersection AJ, okay, what would that be? If both of them have to be monochromatic, then in fact all these, okay, so maybe this is not an example that will be very insightful. Yeah, this is already dependent because probability of both of them being monochromatic is all these 2k minus 1 guys should get the same color, but now same color has two options. So this is the probability. So this is half to the power 2k and half to the power minus 1. Okay, this is 2k, but this also happens to be equal to P of AI intersection P of AJ, right? Because this is half to the power k minus 1. Again, the minus 1 is because of the two colors, and half to the power k minus 1. So this also turns out to be half to the power 2k minus 2. So these quantities are equal. So there is a pairwise independence between these two. Okay, so yeah, but if you try to go to this extreme, then the problem is that if you again have a third edge here, okay, some AK, right? Now, and also this AK was a bad drawing. Okay, so this AK is something which picks one vertex, yeah, something like this. Okay, if you had a edge AK, remember that these two guys are also in AI. So if EJ is monochromatic, right, if EJ is monochromatic, then this and this have this, if EJ is monochromatic, then this and this have the same color. But now suppose, okay, I think I should draw a different example for AJ or AK. Okay, again I am going to draw something which is like this. Okay, so this is AK. So now if EJ is monochromatic, that means all these guys have the same color, and if AJ is non-monochromatic, then you can see that this is surely of a different color because every other vertex in AJ is non-monochromatic, which means you can automatically conclude that EI is non-monochromatic. Okay, so there is a mutual three-wise, there is a dependency here. Okay, so that is why we don't resort to this kind of a calculation. We just prefer to work with different vertex sets altogether. Okay, that's only a remark. Let's get back to our next example, the last example for this lecture. This is about exact K-SAT problem. Quick recall. What is a K-SAT formula? It's a and or a conjunction of M clauses, C1 and C2 and etc. Cm. That's the formula you are checking whether it is satisfiable or not. each clause is a disjunction, an OR of k literals x1 or up to xk, and all these literals, each literal is either a variable or its negation. Now all these variables, we assume they come from a large set of variables V of some size n. There are n variables, m clauses. Each variable can go to different clauses. We say that phi is satisfiable if among the 2 power n truth assignments you can give, each variable you can set to either true or false. If at least one of that assignments, under at least one of that assignments, if phi evaluates to true, then we say that phi is satisfiable. And do you recall what was the result that we got? Actually, it is actually good if you do not recall, because it is easier to remember the method, what we did, rather than what we actually got. So if you remember what we did, then we can always redo that and find out what was the result we got. That way it's easier to remember, okay? Whereas if you remember the result but forgot what you did, then you cannot always recreate that. So the random experiment there was assigning the true or false to each variable independently and uniformly at random. We said that the probability that a clause is satisfied is very high, in fact, right? Because if it has to be unsatisfied, since it's an OR of guys, every literal has to work against you, which happens with a probability half to the power k. So with 1 minus half to the power k, which is your p, which is a very high probability, each clause is satisfied, which means the expected number of clauses that you are satisfied is a very high fraction of m. We actually worked with k equal to 3, in which case this p was 7 by 8. So we concluded that 7 by 8 of the fraction of the clauses can be satisfied in any 3 set, exact 3 set. Okay. Here we needed each clause to be exactly 3. And also we needed some sanity checks, like 2 variables do not appear in either the same form or different form here. Okay, that was also there. But this is the result that we got. Okay, something like this number times m would be the number of clauses that can easily be satisfied. In fact, there is one assignment which satisfies at least that. But we really did not speak about satisfying all the clauses, or phi, the whole of phi being satisfied. Why didn't we do that? Let's see. If we had applied the union bound, what would we get? What is the probability of the bad event, that phi is not satisfied? We can upper bound it by the union bound, or this is the union, even if one of the clause here is unsatisfied, right? So phi is unsatisfied, so it's a union of all those bad events, each bad event ci being the event that ci is not satisfied. But now not satisfied had a probability that is upper bounded by 2 to the power minus k. Okay? This is a very good probability, right? 2 to the power or good in the sense is a low probability. This q is 2 to the power minus k. Remember, this time we are talking about probability of not satisfied. P was for the probability of it being satisfied. Okay, so not satisfied is 2 to the power, or half to the power k, I should say, 2 to the power minus k. And now the union bound will give you some m times q. So if m times q was less than 1, we could have said something interesting. But what is interesting, that phi is satisfiable, right? If mq was less than 1, we could have said phi is satisfiable. But for mq to be less than 1, we want m to be less than 2 to the power k. Okay. 2 to the power k sounds good when k is very large, but still we are only saying that like for small things like 3 sat, we are saying it is like you have less than 8 clauses, or even for 10 sat we are saying that we can have at most 1023 clauses. Okay, so which is only a constant for a constant k. That's why we did not make that claim, even though we could have easily made that. But now let's say whether there are scenarios where we can apply the Lovasz local lemma, and in fact such scenarios are very common. This is very much connected to that hypergraph case also, so the resemblance is not artificial. Suppose each variable appears in at most L clauses. Okay, so in some sense this is like if you look at the degree of a variable, if you can see what it means, we are saying that the degree of a variable is at most L. This has a formal picture to it. You can imagine the variables as you can imagine a bipartite graph with variables and clauses. So you have n variables v1 to vn, right? And you have c1 to cm, some m clauses. Okay, m can be much larger than this, and each variable, when it appears either in its form or the negated form to a clause, you add an edge like that. Okay, And what we are saying is that this degree, when you look from the variable side, for any vertex is at most L. Okay, so that's why in some sense is also a degree. Yeah, so and this is called the incidence graph of this formula phi. It's a very useful structure to know. It's a bipartite graph which captures just the incidences. Looking at the graph, you do not really know whether the variable appears in the as itself or in the negated form. You can kind of encode that by giving a different color to these edges if you want. But in this problem at least that's not important. So each variable appears in L at most closest, right? Then I claim that, this is an important claim, I make this claim that each clause is mutually independent to m minus this number, k times L minus 1 other clauses. Okay, this I want you to pause and draw a picture like the one we did for the hypergraphs and convince that this happens. Okay, so I'm assuming you have done that. Again, you look at any particular clause C that has some k variables, Now, each of those k variables may appear in L minus 1 other edges, right? Each of them may appear in L, because each appears in at most L clauses. This is already one clause, at most L minus 1, you have k of them. So there are some at most k times L minus 1 other clauses which have some intersection with this guy. All the remaining clauses are from a different planet. They are constituted of variables which do not even make an appearance here. Okay, so you can claim mutual independence from all of them. So the degree of this dependence graph that we are talking about is k times L minus 1, and hence what do we need? We need EP times, this is the Lovasz local lemma condition. If this is satisfied, phi is satisfiable. Again, here what I want you to pay critical attention is that there is no m appearing here, you only have the d appearing here. Okay, now it's just substitution. Your d plus 1 is this, d is nothing but this d is what I am replacing with k times L minus 1, and because finally I want to get a bound on L, okay, or an L that will satisfy this condition, right? So we can, after this is a very easy calculation, I am not going through the details. You see that if your L is at most this, maybe approximately, if L is at most this, then this condition is satisfied. Okay, then you get this condition to be satisfied. And hence from the Lovasz local lemma you can conclude that the union event has probability less than 1. The philosophy remains the same. Okay, so in particular let's just apply this L equal to 10. Okay, then this bound that L needs, not L equal to 10, sorry, k equal to 10. Okay, so let me apply the bound. Yeah, E10 sat. So this means k equal to 10. Then 2 to the power 10 by 10k by ke. 10e is something like 36, right? So we can make a statement which says every E10 sat, that's a clause in which, that's a formula in which each clause has exactly 10 variables. And if you have an E10 sat formula in which each variable appears in at most 36 clauses, then it is satisfied. Now this 36 is a constant, I agree, we cannot come out of that, but still the total number of clauses can be very large. Okay, that's the major difference. In fact, these kinds of clauses are also well studied. In fact, we know that E3 sat in which each variable appears at most 3 times. Variable appears in at most 3 clauses is NP hard to solve. NP hard to check satisfiability. Okay, but if you substitute k equal to 3 here, you will get something like 2 to the power 3, 8 over 3e, which will be less than 1. So yeah, it does not, this does not help you with that. But even for moderate k, like 5, 6, 7 something, you can rule out at least certain clauses. You can say that they will be always satisfiable by using this result. Okay, yeah. So that is the Lovasz local lemma. at least in the beginning, try to set up the same way as you would set up a union bound proof, but instead of using the union bound, try to see if you can control the dependency, the degree of the dependencies, or control the dependencies and use the Lovasz local lemma. Okay, thank you.